Hello everyone, my name is Ruei-Che. I'm very pleased and honored today to talk about my master thesis work at Dartmouth College. The title of my talk is Accessible Circuits, Adaptive Add-on Circuit Components for People with Blindness or Low Vision. I would like to especially thank Xing-Dong and Ruei-Che for guiding me through the project. I would also like to thank my colleagues Wen-Ping, Yan, Zheer, Chi-Huan, and Justin for their hard work. Let's see how Accessible Circuits works. The breadboard extension works with commercial smartphone and has tactile labels that mark the R columns of the breadboard. Users can locate specific columns using them. The labels and breadboard components are conductive, so the smartphone can register the physical contact from them and give audio feedback when a component is inserted. There is also vibration feedback from smartphone when a wire is inserted. To understand the accessibility barriers, we began by a formative study with 10 blind participants. We tested some of the commonly used components and tools as shown in this figure, which includes several basic electronics, breadboard, and the tools like props and wire stripper. During our study, we asked our participants to identify the tested components and insert the components to the breadboard and connect them using wires, and also understand a finished circuit on the breadboard. We also tested how well the participants could strip wires with different sizes and prop component pins. We found participants could identify the tested components through their shape, number of pins, and how they can be manipulated. However, inserting the components to the breadboard at the correct location is very hard. This is because the breadboard holes are small and hard to be perceived by touch. Another reason is that component pins are too soft to stand the push against the breadboard, making them hard to be inserted. More accessibility issues were illustrated in our paper. To address them, we designed and developed accessible circuits. We created an haptic audio interface that we mentioned earlier. We also created the adaptations with stronger pins that are hard to bend. The proxies are conductive and electrically connected to its corresponding pin, allowing for audio-based interactions through touch. Another useful feature on the component add-on is the wire slots on this side that align with the component pins. This can help the user to count the pins, easily connect a wire, and prop component pins. For the components that have a value like the resistor shown here, we have braille on the side of the add-on to haptically show their value. Lastly, for the components with polarity, like an IC, we use the red dot on the add-on to indicate their polarity. Please read our paper to find out more adaptations, including the ones for a wire stripper and Arduino Uno. To evaluate accessible circuits, we ran another study with same 10 participants. During the study, we asked our participants to identify the components with our adaptations and construct breadboard circuits of two levels of complexity, which is determined by the number of components and wires. As shown in this figure, the top one is a simple circuit, while the bottom one is a complex circuit. Participants were also asked to strip wires and prop component pins using our adaptations. We found that users can still identify the components with a success rate of 93%. They were also able to insert wires and components correctly using the tactile and audio feedback provided by our system. We observed a success rate of 86% for the simple circuit, and 83% success rate for the complex circuit. Our participants were able to correctly prop component pins in 90% of the trials, and strip wires about 83% of the times, which is a significant improvement compared to our first study. In conclusion, in this work, we investigated the accessibility barriers in current circuit prototyping environment for people who are blind or low vision. Second, we designed and developed accessible circuits to address the identified accessibility issues. Finally, we demonstrated our approach could effectively lower the identified accessibility barriers, and our solution is based on technologies that are available to blind community, such as smartphones and 3D printing. Thank you for listening.